My name is Bradley Hostetler. I am AstroPak's metallurgist. I'm part of our technical services group. So we're an R&D team. We assist sales, and we get to do a bunch of root cause analysis when there's any sort of contamination in a stainless steel system. That's my team specifically. AstroPak is a chemical service provider in really any sort of high purity industry. So passivation is our bread and butter, but any sort of forced circulation, alkaline or acid processes in installed stainless steel systems. So I was tasked to speak about protecting hygienic integrity in stainless steel systems. I'm breaking it down into 3 phases. We're going to begin with passivation. What is passivation? Why do you need to passivate? What instances would require repassivation of stainless steel? Then we'll talk about corrosion of stainless. Rouge, corrosion of stainless steel, some root causes, mechanical damage, chemical damage, and then finally land the plane with surface finish. What methods do we have for improving surface finish, and why do we want a smooth, cleanable surface? Best way to begin with passivation is defining it. I am going to mention 2 documents a lot throughout the course of my presentation. They are both ASTM standards, and they've been mentioned a couple times in the last 24 hours. They are A967 and A380. I'm going to start with A380 as a more encompassing specification, going over all chemical processes you can do for stainless steel. Cleaning stainless steel, descaling stainless steel, and passivating stainless steel. A967, on the other hand, drills down and it's specific to passivation. Both of these documents were updated in January. So this is a 4-month-old definition. The other one has existed for, I think, a decade before it just got updated this year. I'm going to summarize it here. Passivation is the chemical treatment of stainless steel with nitric or citric acid solution for the purpose of removing contaminant iron or any other foreign matter from the surface, resulting in an increase in the corrosion resistance of the surface by enabling the formation of a better passive metal oxide film. I highlighted 3 points right here. Passivation is a chemical treatment. We're targeting contaminant iron or other metallic contamination on the surface. And third, we do it because it increases the corrosion resistance of the surface. It ensures the corrosion resistance of the surface by enabling a better passive metal oxide film. Let's talk about that passive metal oxide film. So 304 or 316 stainless steel. We've got about 65 to 70 weight percent iron in there. So it's much less than carbon steel, which is going to be anywhere from 90 to 99% iron, but still, it's the predominant element in stainless steel. The second most included element is chromium, at about 16 to 20%. Chromium exists all throughout the stainless steel in this nice little sketch of a cross-section of stainless, but it primarily migrates to the immediate surface of the alloy. And here it reacts with oxygen and forms a chromium oxide surface, or chromium oxide layer. This is the passive layer. The passive layer is nanoscopically thin. So when we think about the layer of paint on our car, that's 100 micrometers. The 2 to 10 nanometers of the passive layer, it's about 1/10,000th of that. Nanoscopically thin, and this layer is providing the majority of the corrosion resistance that we are selecting stainless steel for, that we are purchasing stainless steel for. A leading metric to determine how resistant this passive layer is something called the chromium to iron ratio. So you take your stainless coupon, you put it under an advanced microscope, and it's analyzing the first few molecules of your coupon. The amount of chromium relative to the amount of iron in that oxide layer in the 2 to 10 nanometers is the chromium to iron ratio. Now the third most included element in stainless is nickel, so that's going to be around 10% depending on your alloy. You see it pop up kind of in between your oxide layer and your actual bulk alloy phase, which is where your composition is going to look exactly how it's reported on the material test cert. We like nickel because it stabilizes the metallic phase, gives you a little bit of high temperature properties, and a little bit of general corrosion resistance as well. Major takeaway here though, chromium oxide is the passive layer, or it's the predominant compound in the passive layer, nanoscopically thin. So we talked about the final part of that definition, the better passive metal oxide film. Let's talk about the middle thing I highlighted. That was contaminant iron. This microscopic metallic contamination is what the chemical treatment passivation targets. So I've got a 200x image right here of a little R&D coupon we use. This is visibly clean to the naked eye. In fact, in the third phase of the presentation, I'll show a photo of the exact coupon. And when I put it under 200x, I found a bunch of microscopic contaminants. This is the contaminant iron, completely unseen to the naked eye. It could be things like iron oxide or rouge particles, metallic iron debris, so any little chips from tool steel. Maybe if we were handling stainless with a forklift and got some microscopic contamination on it that way. Any sort of surface inclusions like sulfides or oxides in the actual metallurgy. And then polishing debris could be it. If we're polishing stainless steel, we're microscopically abrading or cutting that surface so that it smooths out. If you're not fully cleaning off those stainless steel particles that you're abrading, they can become contaminant iron. All of these can be active corrosion sites or sources of rouge down the line, either if they're sloughed off of the surface through the process flow rate, or if they remain embedded on the surface, they are corrosion-susceptible locations that passivation targets. We're going to go even deeper now. This is an Auger electron spectroscopy graph. This is one of the methods you can use to determine the chromium to iron ratio. We are on the x-axis here in angstroms into the surface of stainless steel. So every 10 angstroms is 1 nanometer. We are incredibly small scale here. The y-axis is just our concentration of certain elements. The black line, that's iron. Red line is chromium. Once again, this is a clean coupon to the naked eye. No signs of corrosion. Notice how we've got probably 3 times or more the amount of iron compared to chromium at the immediate surface, even though this is a clean part. When we passivate, the major change is we have plummeted this iron level. So the major mechanism of passivation, the chemical treatment, is the removal of iron on the surface. The secondary benefit, that chromium did go, is about 6 to 8 in the last slide. Now we're at a 10. So our secondary benefit is chromium enrichment in the passive layer. And then third, I'll do a little overlay from the sketch on the 2 slides ago. We get some increase in the thickness here, but we're still within that 2 to 10 nanometer window. So this is about 80 angstroms. That's 8 nanometers. And then just to drive it home, the transition area where we got the nickel dark green line enrichment right there. And then once we're at, what is this, 180 angstroms, 18 nanometers, this is our metallic phase, exactly how it shows up in the material test report. So it's these 18 nanometers that are providing us the majority of our corrosion resistance. To drive that all home, that nanoscopically thin layer is pretty susceptible to damage, whether it's chemical damage or mechanical damage. And these are some compromising actions that can ruin the passive layer and necessitate repassivation. A lot of these are fabrication effects, but also they can occur in just the general use of your stainless steel once it's been installed and up and running. Welding I'll talk about in a couple slides. We'll skip it for now. Construction soils, what we mean with that is just really fabrication debris, whether it's tool steels or debris from cutting and finishing the stainless. And grinding and polishing, I kind of mentioned that before. If we're abrading stainless steel, we have to clean off the either abrasive pad residue or the stainless steel particles that we have cut themselves to make a smoother surface. Finally, corrosion. If we are inspecting stainless steel and we see an active corrosion site, we know that the passive layer no longer exists there, and we are generating iron oxide from that 65 to 70% in the bulk alloy phase. So we know what is passivation, when we may need to do it, what it actually does, fine-tuning that nanoscopically thin oxide layer. Let's talk about what we can use to passivate. On the right side here, this is a bar graph with chromium to iron ratios, kind of showing what you can expect with different chemicals. Up top right here, the clean and oxidation is kind of like an as fabricated, as clean. I mean, I just showed you 3 slides ago that we had something that was 3 times as much iron compared to chromium, so like a 0.3 chrome to iron ratio. 1-to-1 is a lot more expected. The last 2 data points my team collected in like the last 6 months were about we had a 0.7 and a 0.9. So 1-to-1 is a safer assumption than a 0.3. Phosphoric acid, it's great at removing rouge or rust from the surface. We don't see much chromium enrichment for it. So AstroPac uses it in our arsenal, but not as a passivating chemical. Nitric acid is probably the original acid that's been used. What is nice about nitric is that its parameters are quite easy. You run it for around a half hour with no added temperature. It's pretty difficult to put temperature in, or it's unsafe to put temperature into nitric acid. You can evacuate a room if you get any higher than around 140F or 60 Celsius. What's difficult about nitric is it's pretty hazardous. A company like AstroPac, we mobilize to an installed system, so we do not like putting a drum of nitric in a van, quite unsafe to bring with us. Also difficult to neutralize. If you're doing an in situ passivation, circulating that, this cannot go down a sanitary sewer most times. So citric acid, of course, is organic acid, much weaker than nitric, and therefore we need to kind of boost the chemical reaction by either adding more reactants, adding more temperature, and letting it run for a longer time. If we match the parameters for nitric acid, that's a half hour at ambient, it's a 1.2. It doesn't touch nitric acid in terms of chromium enrichment. If we bring it up to about 2 hours at 60 Celsius, 140F, now we're meeting nitric acid. We get some enrichment there. And taking it up to 80 degrees Celsius, once again, nitric should not be used anywhere near this temperature. At 80 Celsius, running it for a minimum of 2 hours, AstroPac is seeing 2.0 or higher chromium to iron ratios. We can also neutralize citric acid much easier, send it down to sanitary sewer most of the time. So that's what we can use to passivate. Let's talk about proving passivation. How do we know that passivation is complete? There are 2 routes you can take here. There's qualitative tests, so that's up top with the iron tests, and then the surface chemistry analyses, that's the quantitative tests you can take. These qualitative checks, of course, go, no-go checks. I show the copper sulfate test on the left side here. It's a surface chemical reaction. You pour a test solution on the surface, and if it changes color, that color change means there is residual contaminant iron on the surface. You don't quantify how much iron you got based on how much color you see. You just know whether or not you removed all of the contaminant iron from the surface. It's a similar story at the Froxel test, just different color change, different time scale for the reaction. AES, the Auger electron spectroscopy, and then XPS below, those both provide you chrome to iron data. The AES, like I showed in the depth profile, shows you how thick the passive layer is as well. Now the coslometer, I have that in the middle. That's a pretty popular device. It's semi-quantitative, I say, because it measures the actual reaction potential, but it is still just measuring the residual iron. You aren't really measuring the passive layer. You're just measuring if any iron was present on the surface, and if the reaction proceeds, then you're in a certain millivolt range for your reaction. Now, as a quality team, I would like that a little bit more because you just write down a number as opposed to take a photo and have it set in your maintenance paperwork, and every time you print it out, the JPEG gets ruined and ruined and ruined, and then you have no idea what color is on the surface. So definite benefit to that test kit as well. Two of the most common techniques to send this acid through stainless steel are going to be the bottom left and the bottom right. So pump circulation. AstroPac mobilizes to customer sites or end user sites. We bring our own pump equipment. We can hook up to a customer or a user pump and send our chemistry through. We also can bring our own steam source so that we provide our own heat. Otherwise, if it's small components that need to be passivated, COP situation, tank immersion is great because it's quite easy to bring heat into a tank. If you have large components or just small spot treatments, pressure spraying or gel application works as well with passivation because you're not going to get the temperature, but you still get the kinetic energy increase for your reaction by agitation or impingement of the pressure washer. So we actually see pretty similar chrome to iron ratios if we're scrubbing a gel into a particular spot or spraying at high velocity onto a surface to passivate. Now, passivation is kind of on one end of the spectrum of acid processes. It's a very gentle acid process. We're removing contamination, the microscopic contaminant iron from the surface. On the complete other end of the spectrum, we have pickling, also an acid process, but far more aggressive. Instead of just touching the contaminant on top of the oxide layer, we are going to dissolve that whole passive layer. We're going to dissolve the transition area, and we take some elements out of the bulk metal phase when we pickle. As a result, we've got chromium in our waste stream, iron in the waste stream, of course, and nickel in the waste stream. That's going to be hazardous waste 90 times out of 100. Also, we are going to roughen finely polished surfaces if we pickle. Now, around the 32 RA of 3A, you should be good, should not experience much roughening at all. But if you're any finer than that, around 20 or less than 20 RA, you will have your surface finish affected and roughened to some extent. As a result, a couple documents in the industry do a good job drawing a line between pickling and passivation. A967 is one of those, and then also the ASME BPE. That's a bioprocessing equipment standard. more in the pharmaceutical space, they do a really good job saying pickling is not a substitute for passivation. Now, language like this exists because if we're pickling, that's kind of our nuclear option. Of course, we're going to remove that contaminant iron that passivation targets. You are just removing so much else on that alloy surface, and you're not getting the same level of chromium enrichment. So that's why they're considered distinct from each other. Why would you pickle? Well, a few folks have put this same graphic in here from AWS throughout the week. Pickling is great for weld scale removal. So that's this color that we see across this big coupon right here. As the numbers increased, there was more oxygen added, kind of oxygen doped onto the weld surface. And this weld heat tint, it is oxidation. It is an oxide layer. It should not be considered a passive layer though. It is iron rich in the oxide, a very poor chromium to iron ratio, and AstroPac typically sees an untreated weld or weld heat affected zone as one of the first spots to corrode in a system. Now, if the weld gets treated, pickling is one of the better options you can use to treat that and remove the color, but any sort of descaling works. So descaling can include media blasting or grip blasting, can include mechanical polishing, so striping out the weld. We've seen a lot of that this week, or pickling. And there's another option for gel pickling because you don't need to send gallons of the very aggressive acid through the surface unless these welds are inaccessible for a gel application. For ASTM 8967, this is their pre-treatment section. The resulting surface before passivation should be free of all of this. So oil and grease, we got to clean before we passivate. Rust, scale is what they are considering, or they define it earlier in the document as weld heat tint or encompassing weld heat tint. So one of the big reasons why pickling still needs to be included in your chemical arsenal, or at least somewhere in the supply chain, if welding generates heat tint. Starting with another definition. So of course, rouge, it's the French term for red. Multiple high purity industries have kind of co-opted this term and made it consider the corrosion product of stainless steel. I use rust and rouge interchangeably with stainless steel. They are both iron oxide contaminations. They appear the same when you take them under an SEM and analyze the elements. You see iron and oxygen. I consider the corrosion product of carbon steel different than the corrosion product of stainless steel, although those are both pretty similar iron oxides. But to me, rust and rouge and stainless steel is pretty interchangeable. Industry has classified, I haven't said defined there, but classified 3 different types of rouge. Now let's frame this kind of slide right here in the context of I am inspecting a vessel, I open up the manway, I see a bunch of color on the surface. First thing I'm going to do is take an alcohol-soaked wipe and wipe that surface. It's a little hard to see, but there's a kind of a clean streak right there. So 100% of that color transmitted to the wipe. This is type 1 rouge. The corrosion source, where the passive layer broke down, is elsewhere in the system. It is not where I'm inspecting it right now. That iron oxide has been generated at a different surface, and it has sloughed off through the process flow rate onto the surface I'm inspecting. The iron oxide compound right there is hematite, ferric oxide, iron 3+. Now type 2 rouge, obviously this is not a tank anymore, but if I take my wipe, I wipe it, and I get some color on the wipe, still color remaining on the surface, that physical difference right there is enough for us to say, this is your active corrosion site, this is where your passive layer has broken down, and this is possibly generating type 1 rouge that is appearing on other surfaces in the system. Notice how it is also hematite. So that's why I call these classifications more than strict definitions of the types of rouge. So very similar acid chemicals can break this down. Type 2 rouge is a bit more well adhered to the surface though. And also notice that the colors aren't particularly strict. Type 2 rouge is typically going to be darker, but I see reds on both type 1 and type 2 rouge. I see any sort of color and any sort of like brightness or shade. Now type 3 rouge, this is where we get different. This is a different iron oxide compound. It's magnetite, so it's got ferrous and ferric iron on it. Typically only seen in high temperature environments like a steam line. This is going to be much darker rouge, black, dark blue, maybe purple. This requires much more aggressive chemicals to remove from the surface. A major takeaway I want to talk about here, it is the chloride, the chlorine ion that is drilling through the passive layer. So that is the chemical attack that is exposing our 65 to 70% iron in the base metal. All ions of chlorine are corrosive to an extent on stainless steel. So this is the chloride, Cl minus, hypochlorite, ClO minus, chlorite, chlorate, perchlorate. All 5 of those ions are corrosive to stainless steel at varying thresholds though. So maybe 100 ppm of chloride will work for you. It's probably going to be less for hypochlorite. So understanding what source of chlorine you have will help understanding the corrosivity of your environment. Here's a snapshot from a textbook I love. I cannot go 2 weeks without opening this PDF of pitting. So that shows where I'm at. One thing I want to bring or drive home here, the chloride's going to break through the passive layer. Once we're forming a pit by corroding that 65 to 70% iron, look at the 2 products of the 2 different reactions that occur. So H+, that's how we measure pH. So we're creating a more acidic environment as the iron dissolves inside this pit. And what's excellent about the geometry of the pit is it's difficult to rinse that out with your process flow rate. So your reaction is going to accelerate as it goes on inside a pit. On the right is a different form of accelerated corrosion, but it looks so similar. That's crevice corrosion. So it's the kind of physical geometry of your environment lending itself or kind of creating stagnation that results in the same sort of mechanism as a pit. You cannot refresh your electrolyte. Your process flow rate's not going to rinse out all this high pH lowering product that you're making, and you've got accelerated corrosion with a pretty otherwise non-corrosive. So I'll talk a little bit more on stagnation. I'm going to be quicker through here because it lends itself a lot to crevice corrosion. But I call it corrosion from an otherwise non-corrosive fluid. So some different sources could be an incompletely drained system that may be caused because of unplanned downtime, or an incorrect, incomplete rinse process. Maybe something happened with your valve sequencing and you left water somewhere in the system. Standing water equals stagnant water. The most common one though, and shown in these photos of a diaphragm valve that failed, is a gasket failure. So you may have a pretty non-corrosive process fluid so long as you're CIPing pretty often. But if you leak through a gasket in a perfect crevice site, that sealing face can be eaten apart over the course of a weekend, I think is actually what I got these 2 photos from. And the stagnant fluids, I mean, rinse water can be enough to generate corrosion. We kind of talked about that with the tap water. So corrosion from an otherwise non-corrosive fluid. So those are the 2 kind of chemical examples that can generate rouge or just break down the passive layer. So let's talk about mechanical damage. These are both examples of ambient water. It's purified water, so there's arguably more corrosivity than with tap water. But the 2 to 10 nanometers of chromium oxide, that can be mechanically worn down. Both of these instances were when a pump was replaced and the horsepower is different than before, and they got too high a flow that exceeded the spray ball manufacturer's recommendation. So definitely always keep in contact with your spray device manufacturer to make sure what's their highest pressure or highest flow out of the orifices. Ambient water right here was enough to create chickenpox on this horizontal tank because it was running 24/7. So it eroded the 2 to 10 nanometers of chromium oxide. That took, I don't know these timescales unfortunately, but I know this one was within a month. This one was much longer, of course, because it was very exacerbated. But if you're not allowing that stainless steel to re-oxidize the self-passivation that it definitely can do, and you're not cleaning it out of whatever was corroding it or whatever was mechanically damaging it, then you can start rouging and generate the corrosion. If you have rouge damage or corrosion damage of your surface, de-rouging, removing of all the corrosion product, is not the full restoration. You're going to have a rougher surface, and it's probably not going to clean the same. It's probably not going to have the same corrosion resistance that you've designed it for as well. Significant damage can even reduce the amount of time before the next corrosion event. So kind of like what I mentioned with passivation. As soon as you've broken that passive layer, now the chromium to iron ratio throughout is much less of a concern, or much less helpful is a better term. So to fully restore a surface, like something that was pitted, that's going to typically require some sort of abrasive process, like a mechanical polish or an electro polish to fully restore your surface finish, fully restore the corrosion resistance. Now this photo on the right, this is not corrosion damage, this is corrosion from mechanical damage. This is like a trough with a 2B finish on it. The RA, I have it saved somewhere in here, but it was definitely within 32. They clean it with 1,000 ppm bleach. It's fine to clean all other surfaces and some of the superficial scratches, but this scratch right here, it was deep enough to where the 1,000 ppm bleach generated rouge. It was not drying quick enough, and just within this scratch, you were having some corrosive chlorine still remain. Taking a profilometer to this, I got an RA across it of 24, and there are other parameters in the profilometer. There's R max, RZ, another one RT that I'll talk about in a few slides. Those were off the charts when I took the profilometer across it, but the average was still fine. So I definitely recommend, if you have a profilometer, to start using other metrics to identify scratches. I think for acceptance testing, RA is a very comprehensive value or comprehensive measurement. And for inspection and maintenance, that's when you can start to adopt some other ones, because it turned out that 1,000 ppm bleach could be measured, or mechanical damage on this order was enough to cause corrosion, whereas the chemical was completely compatible with the rest of the surface, or the surface as they purchased it. A little bit more on roughness. Rouge or corrosion product on the surface can increase your roughness. So I have a pump impeller right here. It was electropolished, and then I got a nice little layer of rouge on it. The clean surface was excellent. It's a 2.6 micro-inch RA. And on the rouge surface, 10 RA. So both of these still well within 32, but we did quadruple the roughness right there, going from 2.6 to 10. So excessive rouge can increase our roughness, and a rouge surface can result in exceeding your surface finish spec, which of course has not happened here, but definitely reduces the time for contamination to appear and remain on that surface. We have probably validated our cleaning to something with a 2.6 RA, or just our clean RA. How do we know that the validated cleaning works on a 10 RA, or something that has much higher roughness right there? So we could reduce any sort of cleaning efficacy if we have a rougher surface than when we purchased it. Now again, with contamination, if we have a rough surface, it's going to lend itself to bacteria to live there a lot easier. So a biofilm can occur when bacteria form these protective clusters on the surface, and it's a lot easier to get a protective cluster if they can find microscopic roughness or microscopic pores on the stainless steel surface for them to live and eventually grow mature enough to slough off bacteria all throughout the water system or wherever on the process equipment. Oftentimes, a mature biofilm may be too strong for normal sanitization practices, and a stronger option with stronger chemical cleaning beforehand may need to be used to fully remediate a mature biofilm. I'll go quickly through here of just kind of setting up a mitigation plan in-house, so you don't need to call a company like AstroPac to come and derouge. It first starts with identifying the source. So I kind of broke it down to, is it mechanical or is it chemical damage? Ultimately, rouge has to be generated from a corrosion reaction, so it's always going to have some sort of chemical as a factor, but the contributing factor, the predominant force, may be mechanical. The cause, was it caused by an operational excursion? Did temperature go above your alarm for a couple hours and that was enough to accelerate a reaction more than what your maintenance is comfortable with or used to? The system design, was an incorrect alloy replaced, or did you replace a component with an incorrect alloy? We had an issue with galvanized being used instead of stainless at one point about 1.5 years ago. They look pretty similar, but not fully similar. Or gasket selection. Was the wrong gasket used when replacing your seals? And then also the maintenance practice, kind of like with that 1,000 ppm bleach. Are we going just a little too close to the corrosivity limit of our stainless steel? Are we not rinsing well enough? Or are we cleaning in some stagnant areas that are just a little bit too difficult to clean? The remediation plan, that really depends on how much uptime you have and how much you're processing. If you're processing 24/7, a time-driven system is essentially a throughput-driven system. But if you're not processing 24/7, once you understand your rouging and your corrosion situation a little bit more, you can lead it to be every X batches instead of every X months. So that you're a lot more proactive with understanding your limit of contamination. And also understand what chemicals you have in-house to possibly perform your own derouging. Derouging, or AstroPac's derouging blends, are pretty similar to what different chemical providers sell for acid cleaning. We're just at a lot stronger concentrations, but speak with your chemical providers and see if they have any options that can remove rouge so that you can handle this all yourself. And this phase with a little spectrum of all the different chemical processes. I got my disclaimer right here. These are at use concentrations. So 100% of a lot of these chemicals is going to be corrosive with stainless steel. But I put alkaline cleaning on the far end at use concentrations of sodium hydroxide at 1 weight % or less. It's really not going to cause any corrosion. Passivation, the gentle acid process, while derouging is a little bit stronger, and then pickling is the strongest, just to show that these are distinct processes, even though it's all acid cleaning processes for stainless steel. Surface finish will be quick through here. Why do we want low roughness? Why do we want a smooth surface? It's high cleanability. I mentioned that a couple slides ago with rouge, but the peaks and valleys in stainless, they can harbor any sort of contamination. Rouge, metallic contamination, the contaminant iron, or even bacteria. This is a 2B finish right here. This is the R&D coupon I mentioned on like slide 2 with the microscopic particles of iron on it, the like 40, 25 micron particles. Pretty clean to the naked eye. Here it is at 200x. Those are the microscopic peaks and valleys of kind of the mill finish line. The smoothest, most cleanable surface is with the mechanical electropolishing combination. Here's just some finishes showing kind of as received after mechanical polish, and then electropolish gives you that clean, featureless, mirror-like finish. We can remediate pitting with mechanical polishing, clean up welds with EP, or mechanical, both of them as well. Remove excessive amounts of rouge, and then of course, we want to polish to meet the surface finish requirement. Here's a slide on measuring roughness. We've seen this a lot before, but RA, it's kind of the average of the amplitude of your peaks and your valleys. I also have RT, which is sometimes called RY. That's your tallest peak to your lowest valley. So it's pretty good at evaluating a scratch. In this example diagram, though, that's not a scratch. The tallest peak is far away from the lowest valley. So you gotta understand what your profile looks like. We're gonna skip this one. The grit sizes and kind of the typical finish that you see, this is all pretty loose right here, but the major point is that your mechanical polish is gonna give you the majority of the RA reduction. It's gonna be pretty smooth if you go to a high grit. The electropolish is a featureless surface. Here are some other high purity criteria. So 3A, it's gonna be at the 32 RA max. Bioprocessing equipment, so that's pharmaceutical world, that's below in the blue. This orange right here, this is semi-F19, so it's electropolished components for semiconductor manufacturing. They have the smallest goalpost that I've seen in high purity industry. So they're gonna do that RY, the RT, highest peak to lowest valley. They're gonna do an average RA, and then a not to exceed within their average RA as well. So they've got the highest requirement I've seen, and then in pharmaceutical, you got 3 mechanical polish options, 1 through 3. 3 matches 3A pretty well, and then 3 electropolish options, 4, 5, 6. I'm gonna skip this one, but if anyone has come across issues with like a black wipe test on a polished surface, AstroPak is identifying this as polishing artifacts, explaining the electropolishing technology. Think about path of least resistance for these electrons. The anodic film that gets made is a resistor, so the electrons want to go up to the microscopic peaks so that they have the smallest jump across the resistor. So that's where the material separates, it ionizes, and so all these peaks get reduced down to the valley level. We're removing material when we electropolish. It's a controlled removal because it's going to be the peaks only till they get to the valleys. You'll see it actually be described as electropickling, but it's a much more controlled process to get you a smooth surface. To drive it all home, here's the final slide. Is passivation necessary after electropolishing? It is not. A lot of documents, a lot of standards do say that electropolishing is sufficient for a chromium-enriched passive layer, and that is true, but we do see passivation following electropolishing as an increased benefit to chromium resistance. So if you are interested in maximizing the chromium to iron ratio, electropolishing is what you want for your surface roughness benefit, and passivation on top of that does increase your surface chemistry benefit. That is all. As a quick plug for AstroPak, our bread and butter is kind of in the top row right here. Passivation through installed systems, derouging, removing the corrosion product, or any biofilm remediation. We can bring any sort of chemical, mobilize with it, and flush it through an installed system. A few other options down here that we're involved in somewhat. Thank you all very much.